We will now talk about higher order movements for poison point process. So we have learnt about first order movements of PPP of point processes. So first order movement is nothing but the measure or the intensity measure, which gives you for any set A, it gives you the expected number of points in set A. So capital lambda A is defined at expected value of phi A, which is the expected number of points in set A. And this measure admits a density lambda x if for any set A, capital lambda A is equal to integration of lambda x dx over set A. So one dimensional example, I have listed some example. If you have no lambda u, the intervals in this would be of the form 0x or some countable intersection or union of such sets. So lambda of 0x is equal to integration of lambda u du from 0 to x. In this case, you can compute the density just by differentiating the intensity measure. So if your density is k, then the mean measure is kb minus a. For any 0x, it will be kx. So you can actually remember some of these cases so that you can quickly identify the corresponding density and the intensity measure. So in this case, you can see this k where density is constant is a homogeneous case, and this will give you the mean measure of k into size of while 2kx will give you something where the density is increasing with x, so the mean measure will be proportional to x square. If we consider 2D example, let's say isotropic example where the density does not depend on the angle. In that case, if I take a ball of 0, r, then the intensity, the number of points in this set would be equal to 2 pi integration of lambda r dr. So in that case, if you want to compute density, you have to differentiate this expectation measure and then divide by 1 upon 2 pi r. So in this case, if you take k by pi as density, then the corresponding intensity measure of the ball would be ki square. This is homogeneous case. Similarly, if your density is increasing with r, then you get something of higher orders. So now you can observe that uh, density from a constant, then it's a homogeneous case, but that does not necessarily mean the intensity measure will be proportional to x or x squared. It depends on the dimension also. So for any d dimension, if the intensity measure is proportional to r to power d, then you can say probably this is a homogeneous case. Now let us come to the second moment. So first moment is defined as the expected number of points in set A. The second moment is actually defined as expected value of phi A square. Right? Expectation of phi A was the first moment. Phi A square of expectation is second moment. Uh, and if you want to write this down, phi is in summation of indicator xi belongs to A multiplied by summation of xj belongs to A. Right? There are two FAs, and if you multiply them, you get many pairs of xi xj where xi belongs to A and xj also belongs to A. This we denote as capital lambda in the superscript. I have written 2 just to denote this is a second moment of A cross A set. Similarly, I can also define lambda to A cross B, which is nothing but expectation of phi A into phi B. And if you write down the expression of phi A and phi B and you multiply them, you get the summation over all pairs of xi xj belongs to phi, where xi belongs to A and xj belongs to B. So you note that in this case, if A and B are overlapping, there may be cases when xi belongs to A. Some pairs are doubly counted because they will also appear when x1 belongs to A and x2 belongs to B. And they will also appear when x2 belongs to A and x1 belongs to A. So if I avoid double counting, I can define something on factorial second moment, which is defined in the following format. I put exclamation mark here to distinguish this from the previous second moment. So for any set A, the factorial second moment of A cross A is defined as expected number of points or expected number of pair, says that the pair first point belongs to A and the second point belongs to A also, and these two ends are not equal. Similarly, you can also define for A cross B. So lambda factorial moment of 2A cross B is defined as expected value of pairs such that the first end belongs to A, second end belongs to B, and xi and xj's are not equal. We can compute these values for PPP case using the method we discussed in the Campbell-Mackay when we were discussing Campbell-Mackay theorem, and you can show that this for a homogeneous case this is equal to lambda square into size of A into size of B. Okay, we have done this exercise. So for A crosses this will be equal to lambda square of into size of A square. Now, what is the relation between the factorial second moment and the regular second moment? You can basically take this summation and then write them in two parts. One where the pay xi and xj are not equal, and then plus all the remaining terms where xi and xj are equal. Okay, so summation over all xi uh, which are equal to xj indicator xi belongs to A. And if you compute the write the expectation on both terms, you will get the following relation that the second moment of A cross A is equal to factorial second moment of A cross A plus mean number of points in A. Similarly, for A cross B set, you get mean number of points. Second moment of A cross B is equal to factorial moment of A cross B plus mean number of points in A intersection B. So from the second moment, we can also compute the summation over pairs. So summation of function over pairs. Suppose there is a function from RD square, RD cross RD to R plus, which takes two input xi and xj and gives you one value. And if I want to compute its expectation over all pairs, so I'm going to go to all pair of xi xj, compute this function on the pair and write their summation. And if I ask what is the expected value of that, that will be given by integration of fxy over the second moment measure of dx comma dy. Similarly, for the reduced moment, for the factorial, for summation over the non-duplicate pairs, then I'm going to get all pairs such that they are not repeated. And then I want to compute expectation that will be given by fxy into the second order moment of dx comma dy. Sorry, second order factorial moment of dx comma dy. Now, if the second moment density exists, which is lambda factorial 2 x comma y, then the second moment of factorial 2 of dx comma dy would be given by density into dx into dy. So for any set A and B, this factorial second moment of A cross B would be given by, if I integrate the density over set A and B. Similarly, for you can also define higher order moments uh, in the similar fashion. And similarly, you can also define the density. So if the density exists, then the higher order moment of any set of A1 cross A2 cross AN would be given by integration of the density over these sets. Note that the density does not exist for the normal regular second order movement, because there we are counting some pairs twice. So if you imagine for A cross A, there would be a line of 45 degree where the points are repeated. All the points in this line are repeated because they are also counted once. I mean, these pairs are actually equal, so they will be counted twice. So that's why when you differentiate it, you get a discontinuity. That is why the density does not exist for the regular second movement, but for density only exists for the factorial second order movement, and that's why we called it density as second moment density. If a process is a stationary and motion invariant, so let's see how does the second moment density will look like for that. So if the stationary something is stationary process, then the second moment density would be just a function of x minus y. They will only depend on does not depend on the absolute location of x and y, but they're just the relative location of y and x. If it's a motion invariant process, then also this only depends on the uh, magnitude of the difference, not the angle of the difference. So for homogeneous point present case, this that's why this will the second moment density would be just lambda square. Let's talk about pair correlation function, which is another way to characterize the second moment. A pair correlation function of any point process defined as gx comma y is equal to the fact the second moment density divided by the lambda x into lambda y, the first moment density of at x and y. And for the stationary motion event process, this will be just a function of r, and this will be constant lambda square. So the pair correlation function will also be a function of r. If pair correlation function actually kind of tells the second order characteristic of the point process, and in particular, if it is more than one, then it shows there is a clustering. It means condition that there is a point, conditioning on that the occurrence of a point at some location increases the likelihood of other points also being there. If GR is equal to 1, this means it's a PPP, which means complete independence. And if GR is less than 1, this means condition that there is a point at 1, it reduces the likelihood of other points being there. So it reduces, it kind of denotes the repulsion in the points. Now we will define K measure of stationary processes. This is similar to the second order moment, but there is some difference between the two. So if I look at the expected value of number of distinct pairs, that is equal to integration, expected value of the summation of a function on distinct pairs, then it is equal to integration of fxy over the second moment density dx comma dy. Now let us put, instead of y, let us put x plus u. Okay, I substitute x plus u instead of y. So this will be dx x comma du. Right. Now this is also a measure which kind of tells that given a location x, what is the expected number of points, x number of pair, such that the first pair is at dx and the second pair is at interval du, x around x. Okay, so we can denote this uh, measure as here. This just means the measure at dx comma du is denoted by the second order density of dx comma x plus du. Now this moment is invariant of the shift with respect to the first coordinate. If I shift this thing, because the second will also shift, so Any measure which are invariant to a translation shift are a multiple of Lebesgue measure. This means I can denote this as a product of the first measure into the second measure, which is lambda dx into k of du. So I'm denoting the new measure as k du, such that the number of pairs in this interval dx into du is given as total number of points in the first set multiplied by some number which depends on the second set. So therefore we can write this equal to lambda fx x plus u dx into k du. Now let us see how we can compute the value of k du. So let us take the example of this function fxy, which is equal to indicated that first point belongs to a and y minus x belongs to b. Right? The difference between y and x belongs to b. So if I put it here, what I get is lambda. If I put it this back into this expression, what I get is indicator x belongs to a, indicator x plus u minus x belongs to b, because x plus c. So I put y minus x plus x, y minus x plus u belongs to b dx k du, and this cancels. So and what I get is indicator x belongs to a, indicator u belongs to b dx k du. Right now I can separate out the terms over integrate x and u. So I get lambda into integration of indicator x belongs to a dx and indicator k du. From this I get this will be equal to k of b, and this will be equal to lambda into size of e. We can let's try another approach using Cabell-Maclay theorem. I can also denote this as a set of two summation, one on xi and second on xj not equal to xj, not equal to xi. And then I can apply Campbell theorem. I can take this as a function and apply Campbell theorem on this one, because this whole thing is a function of xi and the whole point process except xi. So this will be equal to integration of the reduced palm probability expectation of gx comma phi dx. So if I put it there, what I get is EE672A factorial in summation over all points xj, x belongs to a, and xj minus x belongs to b dx. Okay, now this summation I am integrating on a whole set, but there is an indicator x belongs to a. So this means this is just an integration over a. Right, I can take this integration, which is one only in the set a. So this integration will be on only a, and I will get rid of the indicator. Right. Now note that this is a stationary point process. So shifting does not change the distribution. So I can define phi dash, which is equal to phi substituted as minus x, and both will have the similar distribution. This means uh, if phi dash, if there's a point at x, then phi dash will have a point at 0. Xj minus x will become xj in phi dash. So this integration will become yeah. So that's why I can write this, that phi dash. This is another way to write that I've taken phi dash s instead of phi, and then denoted as 0 dash on this one. So what I get is basically you can say that for xj minus x will be some point yj belongs to phi dash, and x point conditioning on x will be same as conditioning on 0. So what I get is lambda into expected palm expectation of condition on 0 of indicator yj belongs to b, yj belongs to phi dash. Now this will have the same distribution as phi, so I can just denote it. I can replace phi dash by phi again because they both have the same distribution, and this will be nothing but the integration of lambda 0 factorial phi b dx. Now if I compare the two, I can say that the inner part is equal to this one, which is kb. So kb is equal to expected value of phi b, condition that there is a point at 0 without counting that point. So this means kdu actually signifies the expected number of other points in a small area du at distance u, condition that there is a point at x. Okay, and then this distance is from related to the point at x, right? Remember, there was x and y earlier, and then I have converted it to x and x plus du. So this distance is relative to the point I'm conditioning on. Okay, so I can directly write the formula for kb, which is given as, for any set b, kb is equal to uh, you you go to all the pairs, distinct pairs, such that xi belongs to A, and you count how many points are there such that xj minus xi belongs to B, right? I mean the relative distance of xj with respect to xi, that belongs to B. Okay, so this is as such, if xi is at origin, then xj would be in the B. Okay, and I divide it by the total number of points in set A. So I'll get the this mechanism, right? Or I can just condition on that there is a point at the origin and compute how many points are there in a set B. That will give me K. Okay. For Poisson-Point process, I can apply Stirling theorem. So this is equal to just E phi B, and therefore KB is equal to lambda into size of B. Then there is another function which is known as replace k function, which is defined as 1 upon lambda into k of ball 0 comma r. Okay, so I take a ball of 0 comma r for variable r. I compute this, divide by 1 upon lambda. Whatever I get that will is a function of r, that will be the replace k function. Okay, and noting that kb is actually the uh, can be dependent on second order moment. This is also given as 1 upon lambda square, lambda second moment density integrated over the ball. Now lambda kr, here if you look at lambda kr, denotes the total number of points in the ball 0 or around a given point. The condition on that there is a point there. And for two-dimensional Poisson-Point process, this k is given as lambda into size of b, which is pi r square. This is given as lambda pi r square. So replace function is actually given by lambda pi r square divided by lambda, which is this pi r square.